Hi, I'm Laren, this is Knife Steel Nerds. Austempering for Bainite is one of the few secret heat treatments that actually works. You can improve steel performance with Austempering. I will tell you what that is, what it means, and how to do it.
So what is Bainite and Austempering? What an Austemper is, it's similar to a quench and temper. With a quench and temper, we austenitize the steel at high temperature, like 1500 degrees Fahrenheit or so. Then we quench down to room temperature, or approximately around room temperature, and then we temper at a lower temperature like 400 degrees Fahrenheit, 200 degrees Celsius. Usually that's done at least twice. An Austemper, instead of quenching to room temperature, we quench to an intermediate temperature, like 400, 500 degrees Fahrenheit, and we hold there until it transforms to a phase called Bainite. Bainite is similar to our normal quench and temper martensite. In fact, without electron microscopy, it can be extremely difficult to differentiate between tempered martensite and Bainite, but they can have different properties in some important ways. So I'm going to talk about salt pot heat treatments that I did for Austempering. And I'm going to talk about how to Austemper different steels and whether the properties are better for bainitic microstructures as opposed to tempered martensite microstructures. Now, like in my last video about austenitizing in salt pots, I used my same even heat salt pot. This is the 709, but in this case, I used a second pot that I have, which is filled with low temperature salts that I bought from High Temp Tools. These low temperature salts have a melting point of about 275 Fahrenheit, and the working range is supposed to be 315 to 650 Fahrenheit. And that allows us to quench and hold at these intermediate temperatures. The salts are fast enough for quenching most materials as long as the steel isn't too thick. The cross-section is small enough. So we can quench down to that intermediate temperature and hold for Bainite. Now, why would we want Bainite? Well, the big advertised property of Bainite from Austempering is improved toughness. So here's a chart that is in a bunch of ASTM handbooks, and it shows that 1095 at 53 Rockwell, with a normal quench and temper, they got around 13 foot-pounds in a toughness test, and with an Austemper, they got over 40. So like a 3 times increase in toughness. Now, why would it be that Bainite would be so much tougher than tempered martensite if they're so difficult to differentiate, except for with very fine microscopy? Well, one of the reasons is something called plate martensite. As martensite gets higher in hardness, it transitions from the normal structure called lath martensite to a more brittle structure called plate martensite. It transitions to plate martensite at about 1% carbon, but above 0.6% carbon, it starts to get more and more plate martensite mixed in with the lath martensite. So plate martensite is more brittle, and sometimes when they look at the microstructure of plate martensite, they'll even see little micro cracks inside the plate martensite. So plate martensite is often undesirable because the toughness is significantly lower, even at the same hardness. So if you tempered plate martensite down to the same hardness as lath martensite, the toughness of the plate martensite would still be lower. And so 1095 has 0.95% carbon, so it's right at that point where it can be almost all plate martensite if you austenitize it hot enough to dissolve all of the carbide and have all of that carbon in solution. But even with normal austenitizing temperatures, there can also be significant amounts of plate martensite in 1095, which reduces its toughness. Bainite does not have this issue. There is no plate Bainite. And so you can avoid that plate martensite issue, and that is one of the big reasons. Another reason that Bainite can have higher toughness is because of tempered martensite embrittlement. So if you temper martensite in a range of like 500 to 700 degrees Fahrenheit or so, the toughness actually goes down. So the hotter you temper, the more hardness goes down, and usually the higher toughness goes. But in tempered martensite embrittlement, the hardness goes down, but so does the toughness. And so you get worse properties because your hardness is lower and your toughness is lower. And they may have done that to show the bigger difference between quench and tempered martensite and Austempered Bainite for this 1095 chart, which just really shows an extreme example of how much tougher Bainite can be. Now, another thing on the subject of plate martensite versus Bainite is here is a chart. It's a percent toughness difference between tempered martensite and bainite for different carbon contents. And you can see that as this line approaches the 0.6% carbon or so, where there is all lath martensite and no plate, the toughness difference approaches 0 between bainite and martensite. So they have the same toughness at lower carbon contents. At higher carbon contents, the toughness difference becomes bigger and bigger, and the bainite has more and more of an advantage. One of the disadvantages of bainite is usually lower in hardness than martensite. So if we look at max hardness martensite, like we just quench to room temperature and measure the hardness, even a 0.5% carbon steel is over 60 Rockwell. And once we get to 0.6% carbon and higher, we're talking 64, 65, 66 Rockwell C as quenched. And even after tempering, the hardness can still be over 60 Rockwell. While with bainite, you have to have quite high carbon steel to be over 60 Rockwell, usually a 1% carbon steel often. So while the bainite can be tougher at equivalent hardness, bainite is usually not as hard as martensite. Now, what controls the hardness of the bainite is not just the carbon content, but also the temperature that you austemper at. So the temperature that we're quenching to and then holding. And so if we're holding the steel at like a 600 or 700 degree austempering temperature, the hardness will be quite low, like below 55 Rockwell, even for a pretty high carbon steel. And as we move lower, like down to 500 degrees, 400 degrees Fahrenheit, then we're approaching the 58 to 62 Rockwell range, depending on the carbon content of the steel. Now, when we talk about how to do austempering, an important thing we need to learn about is the TTT diagram, time temperature transformation diagram. It's also sometimes called an IT diagram or isothermal transformation diagram. These diagrams are in some handbooks and data sheets. I have a collection of them in knife engineering that I've taken from various places. This one is for 5200, and they look a little complicated at first. They're not that hard to read, and I'm going to talk you through them. This one is for 5200. One important element of a TTT diagram is what temperature they austenitize the steel at before creating the diagram. So for this one, for 5200, is 845 Celsius or 1555 Fahrenheit. So they heated it to that temperature and held, and then what they did is they would quench to different temperatures and hold and measure the transformation of the steel. Now, we are interested in the lower temperature range, so in this case, something like 500 to 600 degrees Fahrenheit or so. Another important part of the diagram is MS. You'll see MS here on the diagram. That means martensite start. That's where you start to get martensite formation. So typically when you talk about austempering for bainite, martensite start would be your minimum temperature because at that point you're starting to form bainite. So to form bainite, you'd have to be above martensite start to ensure it's all bainite and no martensite. So if we follow the line right at martensite start around 500 degrees Fahrenheit, you can see that we have lines at different points on this diagram. The furthest left line is the transformation start time of the bainite, in this case around 50 seconds or so. Then there is a 50% transformed line, and then a 100% transformed line. So you can see that it started to transform around 50 seconds. It was 50% transformed at around 300 seconds. So between the start and 50% is only about 250 seconds because this is a log scale. So even though the 50% line looks halfway in between start and finish, the 50% is reached quite early on. And then the transformation slows with further time, and then it takes up to 2,000 seconds, around 33 minutes, to be fully transformed. Then on the far right of the diagram, there are different hardness numbers. So they're showing when they austempered right above martensite start at 500 degrees, they got about 58 Rockwell at the end. Now, sometimes it can be difficult to find TTT diagrams for every steel, but you can also sort of make your own transformation measurements. And what you can do is austemper for different lengths of time and then find where the hardness levels off. So here is a diagram showing experiments from a journal article on 5200 where they austempered at different temperatures. So 450, 500, 550, 600 degrees Fahrenheit. And so when they held the steel at the temperature for a very brief period of time and then quenched, it's almost all martensite. You can also just let it cool in air after the Austempering. So they held it for a brief amount of time, no bainite formed, then they let it cool after that, and they formed all martensite. And so they're all around 65, 66 Rockwell because it's fully martensite. This actually has a name. It's called a mar quench, and I'm going to show some results for hardness and toughness on 01 when it is mar quenched. That just means we quenched to an intermediate temperature and equalized so the steel part was all the same temperature before then letting it air cool to form martensite. And the properties can be a little bit different, even when you do that, not forming any bainite. But you can see that the hardness is dropping as more and more bainite formed. So if we held for an intermediate period of time, like 1,000 seconds at 500 degrees, you would have some amount of bainite, and then when you air cooled, the rest of the steel would transform to martensite. And so you'd have an intermediate hardness value. Now, when they reach 2,000 seconds, which is about the same as what we saw on our TTT diagram, then the hardness was around 57 Rockwell, and with further holding time, the hardness was flat, meaning that likely no more bainite or only very small amounts of bainite formed. Now, even if you did get a little bit of martensite that formed at the end, that is easy to take care of. That martensite is untempered, but if we add an extra tempering step, like at 400 degrees, that would temper the martensite, and there wouldn't be any brittle martensite left in the steel. That takes away one of the benefits of Austempering, that you can do it in a single step as opposed to quench and temper where you need multiple steps. But usually it's not that big a deal, so if you're concerned about not being fully transformed, you can add a tempering step after the Austemper. But this is a way that you can determine how long does it take for your steel at your given austenitizing temperature to transform. So your steel, your austempering temperature, your austenitizing temperature, and you can see, okay, the hardness is no longer changing after about 2,000 seconds. Another thing you can do is just make sure you're holding for long enough. All of the experiments I did for this video, I held for at least 2 hours. You know, that period of time is not a big deal for me. If you're trying to save yourself time, you can find the point at which it's fully transformed and not have to have longer austempering times. But to sum it all up, you can find how long it takes to transform by measuring the hardness after different austempering times. Now, to just look at a couple example curves of the transformation, these are the percent transformed at each austempering temperature for different times. And you can see that it forms kind of an S shape where it takes a little bit for the transformation to start, just like in our TTT diagram. Then it transforms, it kind of ramps up, and then it has kind of a period of linear transformation, and then it starts to slow down as it gets closer to 100% transformed. So if you are making your own transformation, you need to pay attention to any small decreases in hardness because you may be at this top of the S, where only small amounts of bainite are forming at that point. Now, I mentioned that the austenitizing temperature is also important, so here's another TTT diagram for L3 steel. L3 is essentially the same thing as 52100, but with a small vanadium addition, usually around 0.2% or so, which helps control the grain size. This TTT diagram, they austenitize the steel at 1950 Fahrenheit, much higher than the 1550 in the prior diagram. And you can see that a couple important changes occurred between the two diagrams. So, in this case, the martensite start, where it was close to 500 degrees Fahrenheit with the 52100 from 1550, now it's around 300 degrees Fahrenheit with the high austenitizing temperature. So more carbide was dissolved, putting more carbon and chromium and other alloying elements in solution. All of those reduce the martensite start temperature. So now we can austemper at lower temperatures. However, the austempering time has also increased. So the kinetics of the transformation, how long it takes for the transformation to occur, is now longer because of that extra carbon and alloy. That makes the bainite take longer to transform. So now, when holding at 500 degrees Fahrenheit, instead of 2,000 seconds to fully transform, around 30 minutes, it's taking over 15 hours to transform. The hardness was also slightly increased. Now this L3 is 59 Rockwell after being held at 500 degrees, where with the 52100 from 1550 was about 58 Rockwell. So there was a small increase in hardness for the same austempering temperature because of the higher carbon and alloy in solution. Okay, now to discuss the experiments that I did. I did experiments with 01, 1095, and 52100. So we'll talk about the 52100 first. I did 1550 austenitizing temperature and a 500 degree Austemper. That was the same treatment we were discussing on the TTT diagram, where 500 degrees Fahrenheit was about the minimum temperature you could use before martensite would start to form. And I held that for 2 hours. Another experiment I tried was 1550 austenitized with a 400 degree Austemper. Looking at the TTT diagram, you can see that this should have about 50% martensite. And then there is this dashed line extending down where they are estimating how long it should take for full bainite transformation after the martensite formation. Now, this is another interesting thing. So we discussed how if you do not fully transform to bainite, you would air cool and form martensite, and then that martensite should be tempered if you want to make sure you don't have brittle, untempered martensite. Another way of having a partial martensite, partial bainite microstructure is to quench under martensite start, but not so low as room temperature, and then you've already formed some martensite, and then you hold to form bainite. And during that hold, you're also tempering the martensite that you initially formed. One thing to note is that some metallurgists disagree about what is transforming at this lower temperature. Some people say that it's not bainite, but it's some type of isothermal martensite. Normally, martensite forms only with temperature. It's called an athermal transformation. The lower that you cool the steel, the more martensite forms. But if you hold under martensite start, you often get a transformation that occurs. And some people call it isothermal martensite. Some people call it a bainite transformation. Some people say it's something else that has some combination of the two, is similar to both. Again, it's really difficult to differentiate between the two, and we're not going to solve that mystery today. In the description, I'll link to a journal article where they talk about the debate, and you can go read about it if you want. Anyway, I tried an experiment where I austempered at 400 degrees, so it should be about half martensite, half bainite after I held for 5 hours, which is longer than necessary, but it should be fully transformed. The other experiment I tried, I used the same 400 degree Austemper, but I austenitized hotter. So I austenitized at 1625 Fahrenheit instead of 1550. Looking at some different journal articles, I estimated this to be the point where martensite start would be just under 400 degrees. Then we would have a comparison with the 1550 austenitized with 400 Austemper. So with the 1625, we would have all bainite, just formed at the lower 400 degree Austemper. So we can compare the properties of the two. Okay, so let's get to the properties. So I've got the 1550 500. That's the pretty standard high hardness Austemper for 52100. I got just over 57 Rockwell, a little bit lower than was shown on the TTT diagram, but not too crazy. The 1550 with a 400 Austemper was just over 59 Rockwell, and had a little bit less toughness. But if we were expecting a big difference in toughness by having 50% martensite, we did not see that in this case. Then when I used 1625 and a 400 degree Austemper, I got just under 61 Rockwell, and the toughness was basically equivalent to other experiments I had done with quench and temper 52100. Now, why would the Austempering not have too much more toughness than the quench and temper? There's a few reasons. One is that the 1625, probably there's a little bit of grain growth with the 52100, which will reduce the toughness some. Another thing is that 52100 does not really have the same level of issue with plate martensite as steels like 01 and 1095. Even though 52100 is also a 1% carbon steel, the 1.5% chromium addition means that you have less carbon in solution after heat treatment, unless you austenitize pretty high. And so it usually has 0.6% carbon in solution, or maybe even a little bit less. And so the improvement in toughness is less in 52100 than the two other steels I'm going to show in just a minute. But this goes to show that where Bainite shines is usually in lower hardness levels than quench and tempered martensite, because if we wanted this same 57 Rockwell of the 52100 with quench and temper, we would probably have to temper at something like 500 degrees, which would be in the tempered martensite embrittlement range. So Bainite can work really well when you want to get a little bit less hardness with higher toughness without worrying about tempered martensite embrittlement. But moving on to 01. 01 is definitely a steel that can have issues with plate martensite. And I have shown that with some prior experiments that I did with 01, where I austenitized at 1550, 1475, and 1425. The reason for the different austenitizing temperatures is if we austenitize lower, we dissolve less carbide and get less carbon in solution, therefore less plate martensite. And indeed, when we compare the toughness, even at the same level of hardness, when I austenitized lower, the toughness was higher. So we want to avoid plate martensite in 01. One of the ways that we can do that is with Austempering. So here is the TTT diagram for 01. It was austenitized at 1450 Fahrenheit, and you can see the martensite start is at about 400 degrees. This is one of the signs that we have that shows us that 01 has more carbon in solution, because this MS temperature is almost 100 degrees lower than the 5200. Carbon has the biggest effect on martensite start. You can also see that it can take almost 5 hours to fully transform 01 at a 400 degree temperature, but that they got about 60 Rockwell when they austempered at that temperature. That's often, a nice round number that knife makers are shooting for. So the experiment I did was austempering at 400 degrees and 500 degrees, and then I measured the hardness and the toughness. I also did a mar quench with 01, where I quenched into the 400 degree salt just for a few minutes and pulled it out and air cooled so that it is mostly martensite. Maybe there's a little bit of bainite to form before I pulled. And we can see if the mar quench led to an improvement in toughness, which is often the reason for mar quenching. You let the steel equalize all at that temperature, so everything cools at the same rate. And one of the big benefits of that is warping. Warping usually happens because the surface is cooling faster than the core. But if we mar quench and let everything equalize at a little bit higher temperature first before air cooling, then the cooling is more consistent and it's less likely to change shape. Another benefit is that with that air cooling through the transformation, sometimes the toughness is improved. So if we look at the toughness results, we see that the mar quench indeed did improve the toughness. It was similar toughness to our 1425 austenitize, even though we austenitized at 1475. Also, the hardness was identical to my conventionally quenched in oil 01 from 1475 and tempered at the same temperature of 400 degrees. When I austempered at 400, so full bainite, I got 59 Rockwell, a little bit under, which is a little bit less than the TTT diagram said of 60 Rockwell, but in the same ballpark, and the toughness was significantly increased over the mar quench. When I austempered at 500, I got 56.5 Rockwell, close to the 56 Rockwell that the TTT diagram claimed, and a little bit higher toughness than the 400 degree austemper. But just like the 5200, I would probably prefer the lower austempering temperature, get an extra Rockwell or two with only a small cost in toughness. Moving on to the 1095, this TTT diagram looks roughly similar to the 01, a little bit less in hardness, closer to the 5200, but the martensite start is close to 400 degrees. Now, when I did only an austemper at 400 for the 1095, and that gave me just over 59 Rockwell, a little higher than the TTT diagram claimed, and the toughness was not as much of an improvement over the quench and temper 1095 as I would have expected. Though I think there is some other limiting factor for the toughness in this 1095. One possibility is cleanliness of the steel. So there are certain impurity elements found in steel. Two common ones are phosphorus and sulfur. So for example, if the phosphorus and sulfur content was high in this 1095, that could be reducing the toughness. Because we are replacing potentially brittle martensite with tougher bainite, but if there are other things that are reducing the toughness, such as a high content of large carbides or a high content of impurities, those are going to be reducing the toughness regardless of what we do to the matrix, changing that from tempered martensite to bainite. And so something else in this 1095 is limiting the toughness, and I'm not sure what it is. but we only got a small improvement, or relatively small improvement in toughness with the 1095 Austempering versus quench and temper. One question some people ask is, should we be Austempering high alloy steels? So far I've only talked about low alloy and simple carbon steels, 52100, 1095, 01. What about a high alloy tool steel? Well, here is a TTT diagram for a T1 high-speed steel. And one thing you notice right off the bat is that the transformation times for Bainite are extremely long. Like if we hold at the 250 Celsius, that's around 500 degrees Fahrenheit, to get to the 90% transform line, we are out at 24 hours, which is quite a long time. I don't know if I want to sit around waiting that long. Another thing to notice is that the hardness is also relatively low. So at that 500 degree Fahrenheit transformation temperature, it says it was about 576 Vickers. Looking at the conversion chart, that's about 54 Rockwell C. At the 200 Celsius line, that's about 400 degrees Fahrenheit, it says 632 Vickers, which is about 57 Rockwell. And according to this chart, it's not even clear that it was fully transformed to Bainite. So if you held it long enough to get full transformation, it may be even lower in hardness. And the reason for this is that high alloy steels are actually designed for about 0.4 to 0.6% carbon in solution. Just like how I discussed 52100 has usually around 0.6% carbon in solution with the extra chromium that's in there. High alloy tool steels have lots of alloying elements, and we typically austenitize them at a temperature where we get in that correct, I'll call it, carbon in solution range, where we have enough carbon in solution for the high hardness that we want, but not so high that we start to drop our toughness with plate martensite. Also, high alloy tool steels can have issues with retained austenite if they are austenitized too high and too much carbon in solution with the extra alloy. So high alloy tool steels, they don't usually have issues with plate martensite. The transformation times are extremely long, and so I think Austempering is not really well suited for these types of steels. So in which cases should we use Austempering? I think Austempering is really great for high carbon steels. So we'll say 80, 85 points of carbon and above, and a relatively low alloy content. Even 52100 does not benefit as much from Austempering. But if you want something in the lower hardness range of like 55 to 59 Rockwell or so, you can have more toughness for a given hardness, even in something like 52100. If you're shooting for 60 plus Rockwell, especially 62 or higher, quench and tempering is probably the way to go, and you can improve your chances by controlling your austenitizing temperature or just selecting a steel which is easier to control the carbon in solution. But Bainite is unmatched when it comes to that little bit lower hardness range, something that's maybe going to do a lot of chopping that needs the toughness and has a geometry that doesn't necessitate so much hardness. But if you have thin slicing knives, quench and tempering is probably still the way to go. But I do want to point out and emphasize that Austempering and Bainite, unlike a lot of secret or magical or special heat treatments, it does actually serve certain purposes and can have improved properties in certain scenarios. And I think Austempering is a relatively underrated and misunderstood method of heat treating, and I think there are some interesting applications for it. So I want to thank my Patreon supporters. With support from Patreon, we're able to do experiments like this, buying salt pot furnaces and low temperature salts and paying for all of these experiments and things. And we can talk about all of the results, and you can learn along with me about how all these different heat treatments work, and we can test different steels. So if you're interested in supporting that, go to patreon.com/knifesteelnerds. Knife Engineering, the book, it has a whole chapter on Austempering. It also has a bunch of TTT diagrams in it, so if you want to learn more, you can also look there. But I hope you liked learning about Austempering and Bainite. Until next time, bye-bye.